So let's start with the first notebook. So this is just the basics on how to work with HiVis, how to load the data, and how the data looks like. So let's just run cell by cell. So I'm using a Jupyter notebook. Of course, you can run it in anything you like. So here we start. So how do we import the data? First we import the HiVis like this. From HiVis, import HiVis. Then we go like this. So we use the new function from the HiVis module, and we specify for it the path for the image. So this is the full resolution image used for Space Ranger. We specify the data folder. So this is the square and something micrometers. So I use the 2 micron, but you can use the 8 or the 16 or the custom one. Also, we specify the path output. This is where all the plots will be saved and all the files if you save them or export them. Additionally, you can specify the properties. You can put here whatever you like. I advise to put an organism, either human or mouse, because this will help you with count of mitochondrial genes and so on. So this is important. Then you create the new object and you give it a name. In this tutorial, I will use the publicly available dataset from 10x of the mouse intestine. And that's it. This is what you specify, and let's run it. So this can take some time because the image is very large and also the data is pretty large. So I suggest to run it on your local machine or the server and not on a network drive because it might take even longer because the files are very large. But anyway, now it's finished and we get this output. This is because we didn't specify here whether to show or not quality control. So the default is yes. So now we can see just a plot of the quality control. So we see the image. So the image loaded properly. So we have on the X and Y axis around 6 microns, which is the size of the Visium HD. We have the mitochondrial percent, number of humis per bin, and number of humis per gene. Okay, so now everything is stored in this SI or small intestine object. So now if we look at this and run, we see that we have this mouse intestine object. We have the organism, the size. So we have 18,000 genes by about 5 million bins. Here we have all the obs that we have in the data. And here we have the var. So in HiVis, all the data is stored in an ndata object. So we have si.adata. This is normal ndata object, which has the obs and vars. Additionally, we have more information. So we have the name, the shape, and the image itself is stored in image full res. You also have a high res and low res images. You have the shape of the object, you have the path or output, you have the properties that you saved, and you have the JSON, which includes the spot's diameter, the bin size, micron per pixel conversion, and so on. Now if you want to access the data, you can access it like this. So you can do just SI and then square brackets and the name of the obs. Or here you can also access genes. So if we run this, we will have the number of humis, and then we pull the number of humis from si.obs. And similarly, we pull from the var and from a gene. So this is how it works. So there is a priority for the obs, then for the var, and then for gene, I think. But anyway, this is very easy to access stuff. So if you just want to look at the distribution of this ApoB gene, you can just do SI and ApoB, and you get the distribution over the spots, which is very convenient. You can also add metadata. So you can do SI something. So in this case, ApoB positive. And let's say I want this positive only if Si ApoB, which is the gene expression, is above 1. So if we run this, we will have false, false, false for most bins, but some of them will be true because they have ApoB inside them. Similarly, we can do, for example, this. So mitochondrial gene. So we can do the var names on the end data. So those are the G names. Dot string dot starts with. So this is basically every mask we want, or we can also specify a vector and just say a string or a number and so on. But this has to be in the same shape of the thing you are trying to access. So for example, here we are trying to access the var, so the vector should be in the same length. And if we want to delete anything, we can just do delete and delete it. So if we run this, we will have false, false, true, true. So those genes in the last, those are the mitochondrial genes. Now we can delete it. And if we now run SI, we see that we have this ApoB positive that we added here, but we don't have the mitochondrial genes, which we deleted. Okay, so now we have this SI object. Now let's subset it because we don't want always to work on the same ROI and the same genes and the same bins. So let's say we are only interested in the highly expressed genes. So let's say we will only have the genes where the number of humides per gene is above 10,000. Of course, you can normalize, then calculate, do whatever you like, but this is just a very simple thing for demonstration. And also, I want to take only the beans that have a certain amount of humides. So in this case, above 1, but of course, above 1 isn't very great. When you start a new SI or HiVis object, there is actually a default number here. So your empty spots will be removed anyways if you don't specify otherwise. So here I will just take pretty much all the bins, but I would just want to show you how you can do subsetting. So if we take a subset now, we just specify the object, we specify the obs. So in this case, we take all the bins that are highly expressed, and then we have all the highly expressed genes. So first the obs, then the vars, similar to undata and so on. And this will create a new object, a new HiVis object. It is not connected to this one at all. And if we want to rename it, we can do dot rename in order to have a new name. If we will not do this, it will just be called like the parent object and subset. So if we run this, we will have this SI subset. Similarly, we can crop it by XY coordinates. So we can do like this. So we can take where the micrometers X below 400 and Y between 360 and 200. So, and of course the vars. But I actually added the new function, which is si.crop, which is far more convenient. If I want to crop a small region based on X and Y, I can just specify dot crop, X lim, Y lim, and that's it. I have a new subset. So yeah, if we do this and run the QC, we will have a smaller object with a much lower amount of bins. So we also can copy stuff. So we can do a copy and it just si subset dot copy. We can also specify a new name if we want. If we will not specify, it will be the same name. So if we do this, we have this new copy of HiVis object. This is a new object overall, not connected to the previous one at all. So now we can, of course, rename it. And now, and this is very important, we can save the object as pickle file. So let's do this. This again might take some time because it's a very large it's a very large file. But after we save it, we can actually load it back by specifying the path. So here you will see after this finished, we will have a path here. This is the pickle file path. So this is the path. So now if I run hivis.load with this path, I will have the object again. This is very useful when running long pipelines because you can run your pipeline, save it, and then later just continue from where you left off. You don't need to run everything again. Now, additionally, you can export stuff from your object. For example, you can export the undata by export h5, and you can export your images and metadata. So this is very important function. If you want to use QPath, which is highly recommended and is big part of the HiVis, I really suggest to use these export images as soon as you want to work with QPath. The reason is when you create a new object, this actually crops all the image that is not used in the image in the Visium HD experiment. So the spots only cover a subset of the image, and in order to save space and time and so on, the image is actually cropped. So if you want to work with QPath, you should do this, export images. If you will not do this, you will also have the cropped images saved in the directory of the original image. But I suggest just to do this. You will have everything in the same place in your output path, and you will have all the images. You will also have a GeoJSON file. Maybe I can show you here. So this is our output folder. You will have this scale factor JSON, which has all the information. You will have tissue positions CSV. Notice that those positions will be shifted according to the crop of the image. And you will have those three images here, the full resolution, high resolution, and low resolution. Yeah. So anyway, so we will have everything this, and then we can go to the next tutorial, which will be about annotations and classifiers.